Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be reviewing branching instructions and how you can translate go-to statements in your simple IR programming language into jump statements in assembly. So first of all, branching. What do we mean by branching? Well, our goal for this lecture is to review, help you understand and be able to do this yourself, how to translate labels and go-to statements in simple IR into labels and jump statements in jump instructions, I should say, in assembly. And as you can maybe see here, unconditional jumps like this are going to be pretty easy to translate. So first of all, what is a label? Well, it's just a named location in the code. We can use labels as markers for points in our code that we want to be able to jump to using go-to instructions in simple IR and jump instructions in assembly. So for here, the way this assembly code would actually run is it would see the label, keep executing, and then move the value 1, the literal value 1, into the RAX register. Now there's two flavors of these branching instructions. The first is unconditional branches. So in simple IR, this is going to be go-tos. In assembly, this is going to be jump instructions. And the syntax for this is just jump followed by a single operand, which is the name of the label that we would like to jump to. Move the program counter to and continue execution from there. So unconditional jumps are pretty simple. What about conditional branching? So here we have some C code we want to try and convert to simple IR to get a better understanding of how this actually works. So we have an integer x we're assigning to the call to readInt. We're checking if x is greater than 10. If it is, we're assigning x to 11. And then no matter what happens here, we then execute x plus equal to 1 and then call printInt passing it x. So let's look at the simple IR translation. So first of all, we declare our function main. At the end of our file, we have our end function as well, and return 0. Every simple IR function needs a function declaration and then return followed by the end function syntax here. We declare our local variables, x and result. We are assigning x to the call to readInt, so same as up here. We are saying if x is less than or equal to 10, go to false label. This is how we can translate conditional branching. So if x is less than or equal to 10, we go to false label. And one thing you'll notice here is that this operator is actually the opposite of what we are using in the C code. So sort of the insight here is that we can actually flip these operators around in order to translate assembly code in a more concise way that more closely matches the original C code or whatever language that we're coming from if we have a language with blocks for managing control flow. A structured programming language, I should say. So for instance here we have if x is greater than 10, do this statement x equals 11. But here we're saying if x is less than 10, go to false label, skip executing x equals 11, and then just do x equals x plus 1. But if x is not less than or equal to 10, it's of course greater than 10. So we don't go to the false label. We instead execute this line of code, x is equal to 11, and continue executing from there. So we would pass the false label, and then execute x equals x plus 1, and then call ultimately printInt. And we're assigning the result of printInt to this result variable because in simple IR, as you might recall, we cannot just call functions without assigning them their values to their return values to a variable. So we have to assign the result of a function call to something, so we have this result variable for doing that. So quick quiz, how do we access the value in a variable in assembly? So for example here, x equals 11, x equals x plus 1, x is less than or equal to 10. How do we get the value of x in all these cases? Here, here, and here, and here. Well, we have to use the symbol table, right? So we have to look at the offset from the stack frame that x lies at. So this is going to be an offset from the RBP register. You can see right here, %RBP. And we see that x's offset is negative 16. So in order to access the value of x, we have to get the value at memory offset negative 16 from RBP. And the reason, again, why this value is negative is because these are stack variables. They're located in the stack and the stack grows down on x86 processors. How do we compare operands is the next question here. So we're looking at the comparison instruction we're performing here. Let me go back to it really quick. X is less than or equal to 10. How do we actually perform this comparison in assembly? Well, we use this comp instruction, and the way this will work is where essentially, let me see if this example here will explain it better. Yeah, so what this comp instruction will do is compare the right operand to the left. You can think of it as if it were RAX is mystery mark RBX, and then it will tell you, basically after performing this comp operation, what that operator would be by using some flags. So for instance, in here, there's some special flags like less than or equal to 0 or overflow and such. The big idea that you need to know is that first we perform a comparison to determine how one variable's value compares to another, and then we perform a conditional jump instruction to jump based off the result of that comparison. So in this case, we say compare RBX to RAX. If RAX is less than RBX, then jump to false label. And I think an example would be very good here, so let's see it. Again, if X is less than or equal to 10, go to false label. That's a simple IR code. The assembly translation would be, assuming RBX and RAX are already set, compare RBX to RAX. We're going to assume RBX is 10, RAX is X, and jump less than or equal, JLE, to false label. This will jump if RAX is less than or equal to RBX. So again, we're comparing we're using the right operand as the left operand in the logical operation that we're performing. So RAX is on the right here in the comp instruction, but it's going to be in the left conceptually when we think of what this JLE instruction, jump less than or equal to, is expressing. So keep the order in mind. Another way to think of this is like subtraction in assembly. Might be a slide here on that. I don't think so. Okay. So remember in assembly we saw there's operators like addition, subtraction, IMUL, multiplication. For sub, we would have, if this was a sub instruction, RBX, RAX, we would say RAX is equal to RAX minus RBX. So same idea. Second operand becomes the left operand logically with what we're doing in the operation. And we can do more than just jump on less than or equal to's. We can also jump in all these different cases here. So not equal, jump less than or equal, jump greater or equal, and then jump equal. So I think hopefully this is somewhat easy to remember, or at least identify based off these mnemonics. So in a quiz and an exam, you might be asked to translate some code or identify the correct translation of some simple IR code. Just remember these mnemonics, and you should be able to do that for conditional branches. And the overall pattern here that we're going to be dealing with is, in the simple IR, we're going to have this pattern we're looking at. If operand 1, operator, operand 2, go to label, then the translated assembly output would be move operand 1 into the RX register, move operand 2 into the RBX register, compare these two values so that RAX is on the left, logically, and RBX is on the right, but RX is going to be on the right in operand order. I know it's somewhat confusing, but this is what we have to deal with this assembly syntax. And then JOP label, and the value of op is going to depend on what the operator is. And they give you an enum in the compiler. For the compiler project in your C++ code, there's an enum you have access to for actually checking what this specific operator is. So it should be fairly easy for you to access this value and check it. It's going to be a field on the context parameter you will have for each of the visitor methods you are implementing. And of course, you have to put the label name as well. Let me go back here. Okay. So another complete example here. If X is less than or equal to 10, go to false label, assign X to 11, and then underneath false label, we say X is equal to X plus 1. So let's translate this one step at a time. If X is less than or equal to 10, go to false label. Let's see the assembly translation. We're going to first move the values of these two operands into the RAX and RBX registers. So assuming that X is at offset -16 from the stack frame, we can access the value of X like this and move it into the RX register. We can move the literal value 10 into the RBX register like so. Then we'll perform a comparison. So we're comparing RBX to RAX. So conceptually, we're putting RAX on the left-hand side of some operator and RBX on the right-hand side of some operator. And then we're going to do a conditional jump to determine whether or not this expression holds for, or inequality holds for some condition. So here we're saying jump less than or equal to false label. So if RAX is less than or equal to RBX, we're going to jump to the false label. Now let's translate this x equals 11 assignment statement. Again, we're moving the value 11 into RAX. Then we're moving RAX, the value of RAX, into the memory location where x is stored. So we're overwriting the value of x this way with the value 11. And in the false label, to translate this, it's literally the same. We just omit a label. The syntax for simple IR labels is identical to the syntax for labels in assembly. Let me zoom out here now for the last part. And for x equals x plus 1, we first have to move the values we are assigning in the right-hand side here, assigning from, so the operands of this operation, into the RAX and RBX registers. So the value of x is going into RAX, the value of 1 is going into RBX. Then we're performing the add instruction here to add RAX to RBX and store the result in RAX, the second operand. And then we move the value that was stored in RAX into the location of memory where x is. And we're getting that location of memory by using this -16 offset from the base pointer from RBP, the stack frame, and we would get this from a symbol table. So you don't necessarily need to do all these moves. Like we could probably, I don't know the exact syntax or requirements on assembly syntax, we probably could pass in memory addresses and immediate values directly to comp. But the reason why we're not doing that is because it's much simpler for you to implement your compiler if we assume we always follow this template of moving our operands into registers first. So here, moving operands into registers and then performing the comparison. Here, moving our operands into registers and then performing the addition. So let's see some examples of translating C code to simple IR now. We won't be doing this in class, but you might be quizzed on this, so I recommend you to at least be able to do this and have the capacity for performing these translations. An if-then-else statement. So I'm going to open up a terminal window here so you can actually see me live code some of this. Let me put my mic down for a second. And I put it over to the side here. I'm going to open a terminal window so we can actually see this, how I would do this. All right, I have two windows open. Let's write some C code that has an if-then-else statement in it. Okay, so we have some C code on the left here that has an if-then-else statement. So we are assigning the value 11 to x, initializing x with the value 11. Then we are saying if x is less than or equal to 10, perform this code here, x plus equal to 1, otherwise perform x equals 0. And then we are returning 0 at the end, so no matter what happens with this branch, this if statement, we are going to always perform return 0. So let's see what the equivalent simple IR code would look like. So we'll assign x to 11 first. And now we have to actually perform our branch instruction here. So we'll say And now we have to have a label that we're jumping to. So what should we use for this label? Well, I'm just going to emit two labels here, a true label and a false label. And now we can actually emit code for the true label to translate this block here on the left into simple IR. And in the simple IR code, we will translate the assignment statement x plus equal to 1, x equals x plus 1 into simple IR because it's pretty much the same way. The syntax is almost identical here. And now to make sure that we don't accidentally execute the else branch, because remember, simple IR code will run one line at a time, we'll need to have another label that we jump to avoid executing the else branch we're going to create, the false branch. So let me write that out here so you can see it. Okay, so what we have here now is a if statement that if x is less than or equal to 10, we go to the true label. The true label is down here. We perform our instruction x equals x plus 1, and then go to the end label. The end label is down here. By going to the end label after executing the code in the true branch, then we are able to avoid executing the code in the false branch. Meanwhile, if this statement is not true, if this if statement is false, we don't go to the true label. We instead execute the next line of code, which jumps immediately to the false label. In the false label, we execute the statement x equals 1, and then we continue executing from here to eventually also reach return 0. So this is a way to equivalently translate the some C code into simple IR. Let's go back to the slides. So next, let's take a look at how we can translate while loops in C code into simple IR as well. So I'm going to translate, change my C code on the left and then change the simple IR code on the right to match. All right, so we're saying while x is greater than 5, assign x to the result of x minus 1. So we're going to decrement x until this statement until the condition x is greater than 5 no longer holds. So how can we implement this? Well, we'll need to use a series of labels to recreate this looping functionality because there are no loops in simple IR. So for the top of the loop, we'll have its own label. And then after the loop, we'll have another label. What the top label will do is actually perform this comparison. So remember, the way we do this is to first move the operands into registers. And let's assume that x is at offset -16 from the stack frame. I'm sorry, we don't need that for simple IR. I got a simple IR confused with assembly for a second. We don't need to do that. Okay, so I believe this is, actually one more line I need to add here. I believe this is a correct translation of this loop. So what we have here is we compare x to 5. Is x greater than 5? If so, go to the true label. True label is down here. We assign x to x equals -1, and then go to the top label. We go back to the top of this loop. We can perform the comparison again. And if eventually it is the case that this if condition is false, we jump to the end label. The end label is all the way down here. We're out of the loop. We just return 0 and end. Now, there's another way to translate this that I want to show. In this case, we inverted the condition. So I don't know if you noticed that, but we swapped the operator to being less than or equal to 5. And now, if we have x being less than or equal to 5 as being true, we break out of the loop by going to the end label. But if this is false, then x is greater than 5, matching what's in our original C code on the left, and then we execute x equals x minus 1, and then we return to the top of the loop. So there's multiple ways to perform these translations. This way of inverting the operator actually lets you write more concise assembly code, but you don't really need to do this. Don't worry about this. In your compiler project, you can have it more closely match the original syntax of whatever program you're writing for assembly, for instance, translating simple AR to assembly. You don't need to worry about flipping conditions around. You can use something similar to this where we are using conditions immediately with these extra labels. And this idea of reducing code by making faster code by having clever translations, clever compilations, is what guides optimizing compilers like Clang and GCC. And there's these kinds of optimizations that speed up your code by removing needless instructions that are honestly pretty trivial to detect. These are called peephole optimizations because it's like you're looking at a little peephole to find ways to optimize your code. So now, the last thing I want to show this lecture is a notion of control flow graphs. So let's take a look at that. I'm going to go over to Excalidraw now to draw a control flow graph example. First, I need to show some code that we can actually draw this graph of. So let me write some code here. And, actually I'm going to just use C syntax here. It doesn't really matter what language we use for drawing the control flow graph, so I'm going to use C syntax. Okay, so we have some code here on the left. If x is less than 10, assign x to 12, return 0. So what would the control flow graph for this look like? Well, the first thing we need to do is create a node in this graph for the operation, for the comparison operation. Then we create separate nodes for a separate node for the condition if it is true. And that contains, this separate node here is going to contain the statement we execute if the condition is true. And then we need to add one final node for what happens after the loop is finished, or the condition is finished, I should say. And then we draw lines to connect these to signify the order in which these operations occur. So you can see this fairly closely, this actually represents directly the flow of control within our C program. So x is greater or less than 10. If this is true, we go to x is equal to 12. If it's false, we go directly to return 0. And then after x is equal to 12, we go directly to return 0 as well. Now what if we change this to have an else statement? Well, we need to update the control flow graph to reflect this other option. And traditionally, false options go on the left, I believe, in control flow graphs, but it may vary on who you're asking or just whose graph you're looking at. And now in this case, notice that we no longer have a arrow connecting the condition directly to the return 0. The arrows we have from the condition, x is less than 10, have to either go to one of the two branches of the if statement, and then both of those branches rejoin at the return 0 statement afterwards. So now finally, let's look at a while loop and how you would convert this to a control flow graph, and then we'll finish this lecture. So in this case, if we execute the code in the while loop, we're going to jump back afterward to the code in the condition. And then from the condition, that is where we might end up going to execute code in, or the return 0 statement, the code after the while loop. So these control flow graphs have applications in security, reverse engineering, compilers, and more. You might receive a quiz question or an exam question on reading these graphs. I won't ask you to write them, but they're a good idea just to know how to write these things. It helps you visualize the flow of control within your program. So that concludes this lecture. I will see you all in the next lecture.